Hello everyone, in this video we're going to consider a double pulley system, so basically a pulley connected to another pulley, which is illustrated in the diagram that I've drawn here. So we've got three massive particles and two massless pulleys, which we're also going to assume are smooth, and the main things that we want to achieve are to find the acceleration of the three masses. So we're going to first find the acceleration of mass m1, and then we're going to find the accelerations of masses m2 and m3, but we're going to find those in a different reference frame. The accelerations of m2 and m3 are going to be found relative to pulley 2, which is of course itself generally going to be accelerating. That just seems like a more natural choice of reference frame to me. And along the way, we'll derive some interesting related results. First of all, the condition for m1 to remain in equilibrium, and then later on the condition for all three masses to remain in equilibrium. So the first thing we want to do as part of our analysis is to draw on all of the accelerations and forces acting on the various particles in the diagram. So we'll start with m1. m1, of course, has a weight pointing downwards of m1g and tension in the string. Let's just call it T, and let's say it's accelerating upwards. So it's going to be accelerating upwards relative to pulley 1 with an acceleration of a1. Now, of course, it could be accelerating either up or down depending on how heavy m2 and m3 are compared with m1. But what we're going to do, just to make sure we get all our signs correct, is draw all of the accelerations pointing upwards, and then if they turn out to actually be accelerating downwards, then we're just going to end up with negative accelerations. So then, because pulley 1 is smooth, there's also a tension T acting over on the other side of the rope which is draped over pulley 1, so there's a tension of T there. And because, I suppose another assumption we're making, which I didn't mention earlier, but which we usually make, is that the strings are all inextensible, and that means that pulley 2 is going to be moving down with an acceleration of a1, or equivalently moving upwards with an acceleration of minus a1. And I want to explicitly write that minus sign in there just to reduce our chances of making errors down the line. Now there's another rope draped over pulley 2. It's a different rope, and so there's no reason to assume that it has the same tension T as the rope at the top, and in fact it can't have the same tension. The tension in the lower rope should in fact be T over 2, and let me explain why. Consider Newton's second law, F equals ma, applied to pulley 2. We have already specified that pulley 2 and both pulleys really are modeled as massless, and so m is going to go to 0. If m is going to go to 0, then F needs to go to 0 as well. The resultant force needs to go to 0, and so if there's a tension of T pulling upwards on pulley 2, there must be a total tension of T pulling downwards. Pulley 2 is smooth, and so that we know the tensions on either side of the rope on pulley 2 are equal, so they must be T over 2 each. If the resultant force on pulley 2 were to differ even a tiny bit from 0, then, if the mass is 0, that would result in an infinite acceleration. Of course, in reality, there are no massless objects, and so the tensions will differ a little bit from T over 2 because there'll be some resultant force on pulley 2, but if the mass is small, then the difference from T over 2 will also be small. So by Newton's third law, that means there's also a tension of T over 2 pulling upwards on each of the masses m3 and m2. Those masses, of course, have their own weights, m3g and m2g, pulling downwards. Now, how are we going to denote the accelerations of masses m2 and m3? Well, we agreed to draw all of our acceleration arrows upwards and just be careful about the signs. Mass 2 automatically inherits an acceleration of minus a1 because it's connected to pulley 2, and pulley 2 has an acceleration of minus a1. So we'll start by writing minus a1 there, but then in general, there's going to be some relative acceleration between m2 and pulley 2 as well. So let's add on that relative acceleration and call it a2. And for m3, the situation is pretty much the same. It inherits an acceleration of minus a1 from pulley 2, but it's accelerating the opposite way relative to pulley 2 compared with mass 2. If mass 2 is going up relative to pulley 2, then mass 3 must be going down because the strings are all inextensible. So it's minus a1 minus a2 for m3. So now we are going to construct our equations of motion by applying Newton's second law to each of the three masses in turn. If we do m1 first, we're going to get a resultant force of T minus m1g in the upwards direction. That's going to be equated to mass times acceleration m1 a1. Let's call that equation 1. We apply Newton's second law to mass m2 next. The resultant force on mass m2 upwards is T of 2 minus m2g. The mass times acceleration term is just going to be m2 times minus a1 plus a2. Let's call that equation 2. And it's much the same story for mass m3. T over 2 minus m3g is going to be m3 into minus a1 minus a2. And that's equation 3. So let's first try and solve this system of equations for a1. That's the first thing that we wanted to do. If we're trying to solve for a1, we basically want to eliminate a2 and also the tension T. Now we can eliminate a2 from equations 2 and 3 by multiplying equation 2 by m3 and multiplying equation 3 by m2 and then adding them together. So let me write that down. We're going to do m3 times equation 2 added to m2 times equation 3. That's going to give you a t term of t over 2 into m2 plus m3. This is going to turn into minus m3 m2g. This is going to turn into minus m2 m3g. Those are of course the same thing. So we've got minus 2 m2 m3g on the left, and that is going to be equal to, for the same reason, it's going to be minus 2 m2 m3 a1. The m2 m3 a2 terms are going to cancel because they have opposite signs. So we just want to multiply the whole equation by 2 to get rid of that fraction. It's going to give us t times m2 plus m3. And it's just going to turn the 2's into 4s. So minus 4 m2 m3g is equal to minus 4 m2 m3 a1. Now we want to eliminate the tension, so we can just rearrange equation 1 to make t the subject and then sub that resulting expression into the t in the equation that we just created. So t is going to be m1a1 plus m1g. So I've just replaced t with that expression at the front, and then all I've done is just expanded the double brackets to get those 4 terms there. So now we've just got to make a1 the subject of this great big formula. Let's identify all of the a1 terms. We've got this one, and this one, and this one. So if we move those all onto the same side, they're all going to be positive. So we factor out an a1, move all of the other terms onto the right-hand side, and divide by the prefactor of a1. And that will give you this expression that's just appeared here. Now that's a perfectly good form to leave our result in. It's quite a nice looking expression actually. There's a bit of symmetry on the top and bottom there. But there's another way that you can write this which I think is kind of cool. So what I want to do is factor out an m1 from the second and third terms on both the numerator and the denominator. So you're going to get 4m2 m3 minus m1 into m2 plus m3, and then the denominator, it's going to be pretty much the same thing but with a plus sign, plus m1 into m2 plus m3. So what I like about this is you can then divide the top and bottom by m2 plus m3. So this will just turn into m1, this will just turn into m1, and then you're going to have the quantity m2 m3 over m2 plus m3, which you might recognize as the reduced mass of m2 and m3. So if we denote the reduced mass by mu, then we can write the expression as 4 times mu 2,3. Let's remind ourselves it's the reduced mass of masses m2 and m3. So 4 mu 2,3 minus m1 over 4 mu 2,3 plus m1, where the reduced mass mu 2,3 has been defined as m2 m3 over m2 plus m3. If you haven't come across this concept of reduced mass before, it's essentially a sort of effective mass that you get by adding together the reciprocals of the individual masses in your system, that appears in various places in mechanics as a sort of overall effective mass of a 2-mass system. So it's kind of interesting to see that pop up here. And of course, as I've just demonstrated, it's very easy to forget that there is a g at the end of all of our acceleration expressions. So don't forget those. So let's just take a moment to consider a couple of implications of this result that we've just derived for A1, because it's the first of the 2 results that we were aiming to derive. So the first thing I want to point out is that clearly the condition for A1 to be 0 is that M1 is equal to 4 times the reduced mass of masses 2 and 3. So A1 is 0 if and only if this equality is satisfied. So this wouldn't have been obvious really without going through all of this analysis, But the idea is that the pulley 2 system, in other words, pulley 2 and masses m2 and m3, can be sort of replaced by an effective mass of mass 4 mu2 3. So if that effective mass is equal to m1, then m1 will remain in equilibrium. But there still might be some relative motion between m2 and m3 depending on their masses. A natural sort of interesting question to ask might be what happens if m1 is equal to m2 plus m3? I'm asking this question because this might have been a sort of naive expectation that we might have had for the equilibrium condition of m1 without going through all of this analysis. So let's suppose that this equality is satisfied, m1 is equal to m2 plus m3. The condition for equilibrium of m1 would then become m2 m3 over m1. What I'm doing there is I'm taking the reduced mass expression and just replacing the denominator with m1. That, of course, multiplied by 4, that would have to equal m1. And then you can rearrange this, multiply both sides by m1, take the square root, and you find that you need the equation root m2 m3 equals a half m1 to be satisfied. Now I find this quite interesting because what this really says is that on average m2 and m3 have to be half as heavy as m1, but when we say on average we don't mean the normal arithmetic mean, we mean the geometric mean, which is the quantity on the left hand side, root m2 m3. So the geometric mean of m2 and m3 has to be half of mass 1 if we are requiring m1 to be equal to m2 plus m3. So that concludes our discussion of A1. Now let's see if we can find A2. We're going to use a similar method, but instead of adding equations 2 and 3, we are going to subtract them to make the A1 terms cancel instead of the A2 terms. We do, of course, need to multiply equation 2 by m3 and equation 3 by m2, like this, and we're going to subtract those. So what is that going to give you? Your t term will be m3 minus m2 multiplied by t over 2. This term and this term are going to cancel because they're both going to be m2 m3g, and you're subtracting them. And then the a1 terms are also going to cancel from the right hand side because they are going to be the same, and you're going to end up with 2 times m2 m3 a2. So let's multiply both sides by 2, get rid of that fraction, turn that 2 into a 4, and as we did before, rearrange equation 1 and sub in the expression for t. That's going to give us m3 minus m2 times m1. I'm going to factor out an m1 here, m1 into g plus a1. That's supposed to equal 4m2 m3 a2. The hardest bit to deal with in this expression is this quantity g plus a1, but we already have our expression for a1. It's this thing over here, and so let's see what happens when we do g plus a1. So that's essentially like adding 1 to the prefactor of g, adding 1 to that big fraction there. Adding 1 to a fraction is the same as adding the denominator to the numerator, right? And so we're going to get 4 mu 23 minus m1, but then plus the denominator, plus 4 mu 23 plus m1. The denominator is not going to change, it's still 4 mu 23 plus m1. Don't forget that g term there. And then the m1's cancel, and you've got 8 mu 23 on top, and 4 mu 23 plus m1 on the bottom, and that's multiplied by g. Notice at this point, by the way, that if you want an expression for the tension t, all you have to do is multiply that by m1, and that is your expression for t. So let's put all of the pieces together and go back to this equation and make a2 the subject. So we're going to divide everything by 4 m2 m3 and replace the g plus a1 with this quantity here. And so we are going to have a factor of m3 minus m2 times m1 at the beginning. Let's put our division by 4m2 m3 there as well. Then we just have to multiply that whole thing by g plus a1, which is 8 mu 23 over 4 mu 23 plus m1, and then g. Now, there are lots of different ways we could write this, of course. We could keep everything in terms of just M2 and M3 and get rid of the mu's, or we could have a sort of mix of M2s and M3s and mu23s. I'll show you the way that I think is nicest to write this. So first of all, of course, I would like to cancel down a factor of 4 and turn that 8 into a 2. Then notice that you've got mu23 over M2, M3. Now, if you look at the definition of mu23, you can see that mu23 over M2, M3 is the same as 1 over M2 plus M3. So that means you can sort of rewrite this whole expression as M3 minus M2 over M3 plus M2. Then I'm going to put my M1 as the numerator of the next fraction. So M1 over 4 mu23 plus M1. Don't forget that factor of 2 as well there. And then g at the end. So there's our result for A2. The reason I like this is that if you ignore this fraction here, what's left is just the result that you'd get for an ordinary single Atwood machine. In other words, just a single pulley with M2 and M3 on either side of it. So we've kind of expressed our relative acceleration of masses 2 and 3 relative to pulley 2 in terms of the simple single pulley result, and it's just modified by this extra factor. So let's consider some interesting implications and special cases of this result. Firstly, I want to point out that A2 is 0 if and only if M2 equals M3. That should be pretty straightforward to interpret, right? It's just saying if the two masses are equal, then there's no sort of preferred side that's going to move down versus move up. So they just sit there and don't move relative to each other. Of course, the whole of pulley 2, the whole pulley 2 system might be moving up or down depending on M1, but M2 and M3 don't move relative to each other if they have equal masses. What about the condition for the entire system to remain in equilibrium? In other words, what if we want to force A1 and A2 to both be equal to 0? That's going to happen if and only if M2 equals M3 and M1 equals 4 mu23, as we derived earlier. So if we combine those conditions, we take our expression for mu23, make make M2 and M3 equal to each other. Let's just call them both M2. Then our equilibrium condition is going to be M1 equals 4 M2 squared, M2 times M2, over M2 plus M2, which is 2 M2. Of course, you can cancel a factor of 2M2 from the top and the bottom, and you conclude that M1 has to equal 2M2. In other words, M2 and M3 both have to be half of M1. Again, that's a pretty intuitive result when you think about it. M2 and M3 have to be the same as each other, but their total weight pulling down has to be the same as the total weight of M1 pulling down. And finally, an interesting special case that I would like to get you to consider is what happens when mu23 is much less than M1, or really 4 mu23 is much less than M1, but if we're considering quantities that are hugely different from each other anyway, the factor of 4 isn't going to make much difference. So that condition would basically mean that this term here, the mu23 term, becomes negligible, and this M1 would cancel with that M1 because the mu23 term is essentially 0. And so you get this particularly simple form of A2. It's going to be M3 minus M2 over M3 plus M2 multiplied by 2g. So how can we interpret what this means? Well, basically what's going on here is that if mu23 is much less than M1, then M1 is just going to fall straight down with an acceleration of pretty much g, right? It's saying the effective mass of 2 and 3, masses 2 and 3 combined, is negligible compared with mass 1. Mathematically, you can see the same thing by going back to our A1 expression. If you ignore this and this, you get A equals minus g. So it's going to accelerate straight down with an acceleration of g. If mass M1 is just plunging down with an acceleration of g, then the whole pulley 2 system as a whole is going to be accelerating straight up with an acceleration of positive g. Now, if you find yourself in a system which is accelerating upwards with an acceleration of g, then you're going to feel a fictitious force downwards, as if there were a gravitational field of strength G. But there is already a gravitational field of strength G, and so to our masses, which are part of the system of pulley 2, it appears as though there's an effective gravitational field downwards of not just G but 2G. So we get the same as the classic Atwood machine result, except we've got double the effective gravitational field. I suppose another interesting special case to consider is what happens when this fraction goes to 1. The condition for the second fraction there to go to 1 is that m1 equals 4 mu 2 3. That's exactly the same as the condition for m1 to remain stationary. So that basically says that if m1 remains stationary, then this fraction becomes 1, and you recover just the ordinary Atwood machine result with just a gravitational field of G, which is exactly what we expect, right? If m1 is not going anywhere, then neither is pulley 2, and so we essentially just have one pulley which is doing something interesting in our problem. So that concludes our fairly thorough analysis of this double pulley system. Hope you've enjoyed this. Thank you for watching, and see you again soon.